But what we're going to do in this session is capacitors in DC circuits. Okay. What is a capacitor? Stores charge, yeah. Slowly, fast, depends on, as you'll find out, we can make it release it slow or fast, depending on other components. Yeah, what's the construction like? Yes. So the construction is we've got connecting leads, two conducting plates, and this green bit in the middle here insulating material, called a dielectric. Dielectric materials can be air, plastics, ceramics, and electrolyte materials. We're not wholly interested in this module in the construction of different types. That's just the basics about the construction. Okay. Right, capacitance. Symbol C. It's measured in farads, not farage. Symbol F. 1 farad, however, 1 farad is very large. So we use microfarads. Because that's around all the farad as a base unit, and if you're going to match it with the other units involved in the calculations like volts, amps, so you've got, because you calculate the farads from the other units, you've got to make them match each other, and then use smaller and larger multiples if necessary. Okay? Yeah. Symbol, Greek letter mu, farad, or 10 times 10 to the minus 6 farads. So 1 microfarad, 1 times 10 to the minus 6 farads, or a millionth of a farad. Nano farad. small n capital F times 10 to the minus 9 farads. And lastly, pico farad PF, commonly known by old hands in the electronics game as puffs, or puffs of capacitance, times 10 to the minus 12 farads. Puffs. Puffs. And if you remember that these two go in alphabetical order, you should always just remember that go micro, nano, pico, alphabetical order. You remember this times 10 to the minus 6, 9, 12. Okay? So that's about how they are and what they made of, or their construction anyway, and how we measure capacitance. Next page. What they do is they store charge. So, if we take a capacitor, like so, and we connect that to a voltage source, like a battery, that will allow a current to flow. Okay. What happens is, over time, and we're not going to worry about how much time at the moment, that's the subject of next week, the charge cycle, or the transient period as we'd call it. Okay, and that's why I've put a lowercase I there, because we could be talking about an instantaneous current over time. That's going to change. Don't worry too much about that at the minute. If we apply 10 volts here, eventually what will happen is we'll have positive charges attached to this plate, because in electricity current flow is actually electrons going in the other direction. Yeah, but they can't travel through that insulating material of dielectric. So for every positive charge on this plate, because that's the positive end of the battery, negative end being negative charge on the other plate. Okay? So let's just make that just a touch smaller. Right over the side. Eventually, VC will be almost equal to 10 volts. Yep. So measuring the voltage across here, eventually we'll get to a point where that's as good, near as damn at 10 volts. And you'll understand next week why I'm saying near as damn at, because I don't ever really actually get all the way there. Okay. If we then take that source away once the capacitor is charged up, we've still got 10 volts across there. So storing that charge. Remove the source, charge remains. Okay, if the capacitor was perfect and all the circuit was perfect in every way, that'd sit there forever. That doesn't happen because some charge will leak away through the dielectric and so on. But you assume that's going to hang around and makes capacitors quite dangerous things in main circuits because they can be left charged up. I mean, the AC mains there 230, but the peak is actually just over 300 volts. So there's a potential on a three-phase system at 600 volts peak. So you need to be careful with capacitors. All right, we'll talk a bit more about that when we talk about the charge cycle. So if we take the source away, the charge remains. Okay. If we then connect another component there, that capacitor acts like a little battery to that resistor, and the current flows in the opposite direction. Of course, what will eventually happen is all these negative electrons this side will travel around the other plate, and that'll equalise, that'll discharge down to 0 volts. Again, over time. And that time, as you'll learn next week, is dependent upon the value of the, in both circuits, the time taken to charge and the time taken to discharge is dependent on the resistor value and the capacitor value. Not on the voltage. Okay? Are you all happy with that so far? Right. Value of capacitance. For a given capacitor depends on three main things. Number one, the area of the plates. Bigger area means higher C. So in some designs, paper capacitors, what they got is two foil plates with layers of paper between them, rolled up and put in a can. That's the way of increasing the area. Yeah. Two, distance between plates, i.e. we're talking about the thickness of the dielectric. But how, what's the, I'll put that in brackets, thickness less distance more capacitance. The closer we can get the two plates together, the more charge it holds, because it's using the fraction between the positive on one plate and the negative on the other. So the thinner that dielectric is, the better. 3. More difficult one to quantify, but the material of the dielectric makes a difference as well. Right, around its electric charge, it will allow, although not very much, the insulator. So air, good dielectric. Yeah, and the biggest example there as a tuning capacitor in an old style rock. What it is a set of fixed plates, because it's a very capacitor. You have a fixed set of plates and a moving set of plates, and what you're altering is as you turn the frequency. So every one of the big old valves that they used to have years ago, if you look in the back, you'll see the tuning capacitor with lots of pins on. Like look almost like the fins on an engine, but one set is fixed, and then between it you've got a set of moving ones, and you're actually varying the energy between them. So that's what the level of capacitance we get from. So the area of plates, the distance between them, and what the material is. That wouldn't be science if we didn't have a bit of maths. C is equal to Q divided by V. Yeah. Coulombs. Coulomb. C-O-U-L-O-M-B-S. C. Farads. V. With a voltage in volts. So it's a bit like an Ohm's law style equation. If we know two of those quantities, we can find the third one. Okay, what you find is that charge quite often Ohm's values are quite often millicoulomb level values. We already know that capacitance is micro, nano or picofarads, and the voltages are generally in the like the 10 or could be, you know, integer style voltages. Also, capacitors charges. So the other way we can get the charges where Q is also equal to I times T in coulombs. Alright? Again, I'll put a lowercase I because if we just connect the voltage source to capacitor, unless we do something about it, the current won't remain constant. As you'll, again, we'll look at that in more detail next week. Yeah. So over time, direct connection of 10 volts to a capacitor will not give you a constant current. Over time, the current will reduce. Okay. So again, we're like linking into next week's lesson in a way. All right. So there's two ways to get the charge. Either it is how much current has flowed over time, and if that current is changing, then that's a tricky calculation because you've got to deal with the current that's constantly changing, which would involve you using calculus. But if we talk about a constant current, 3 amps flowing for 3 seconds, and we can use that formula to calculate the charge that would be after that. If that current kept on flowing for more and more time, then the charge would carry on increasing. The limit to this is, and the other thing I ought to put on this page about capacitors and their units, put it on here. Capacitors also have another part, specification. Anyone remember what that is? Working voltage. So talking about this constant current being applied, keep applying that 3 amps, charge keeps going up. If we look at the other formula, charge carries on going. V here would be charge divided by C. So the voltage is going to keep increasing and increasing. Eventually, we go over the working voltage of the capacitor. What happens when we go over the working voltage? Well, capacitor is 2 plates insulated by a dielectric. Okay, this is an insulating barrier, but every limits. If we push hard enough, it will break. A paper capacitor will blow the can and spread paper everywhere. For instance, goes up big time if you go significantly over voltage. Yeah, but that's because you're applying a fixed voltage and you're going to let the current gradually reduce. Next week we'll cover it in detail. Alright? Yeah. They're quite useful. What you'll find, what you'll learn next week is that the charge cycle, the time it takes to get almost to 10 volts, is a consistent thing, and therefore capacitor resistor circuits are used in timing circuits because they're a consistent and repeatable thing. Find V across 4 microfarad cap when Q (6 millicoulombs). What's what for with here? Yeah. Formula Q is equal to, yeah, we didn't have it in that form, we had it in this form. C is equal to Q over V. Yeah. So V is C, in this case, the minus over 4 times 10 to the minus 6. Charging thousands gives you a charge, pretty big unit as well, and that's an indicator is. Alright. Things to do, and then I'll have a go at the questions and I'll help you along. Like resistor, connect capacitors in combination. Two capacitors in parallel. Right, I apply to that circuit, okay, would end up with the same they've all got the same voltage. Yep. Value, they'd all have the same charge, okay, or they'd all have charges equal to our value times the voltage. Yep. So the total charge QT is equal to Q1 plus Q2 plus Q3 plus Q3. We can just add them all together. Therefore, CT must be equal to C1 plus C2 plus C3 plus Cn. So parallel capacitors are like series resistors. We add their values together to make an equivalent value. Yeah. If we've got mixed multiples, we must be careful with them. We add them together. If they're all the same multiple, they're all microfarads, you can just add the numbers together and the answer's in microfarads. But if they're different, you've got to deal with that with the powers of 10 notation. You got the charge from each of them to cause current to flow. That's why. So if you take that battery away, and connect a resistor, I've got plus the charge on that capacitor plus the charge on that capacitor that will cause current to flow through that discharge resistor. So I'm all the charges added according to the voltage which was fixed, but the value of capacitance could be different, then the overall capacitance you've got there must be all three added. Now, capacitors in series is a whole different. Three capacitors in series, okay, do that and connect them to a source of voltage. What will happen is the current will flow and we plus charges on there, for instance, and for every on there we have a negative charge there. These positive charges here will charge from this 4 is going to leave this plate with 3 positives. Which is going to attract 3 negatives. Taken this plate, the extra 3 positives extra. The current that flows positive cannot go anywhere else to the plate. Do any outside old circuit. Any charge that would, we take the battery away, connect the resistor. The only is make you haven't got there is 200. I've got specific values that up other values. Well, if it's in your tin, but you've got to make it up. It's not very common to connect. I admit it's not very common to connect capacitors in series. Get in there. You can't too off in there. Well, you can, but you're ending up with is you're connecting up across there. You've got a series parallel combination circuit. Yeah. What I'm saying is as that circuit is, this current that flows in here can't flow out there. It's just going backwards and forwards. If you teed off, then that's going somewhere else. It's a completely different circuit. Yeah. So charge in this circuit. There. And for a series, total charge is equal the charge on each capacitor. More importantly, the charge on each capacitor is equal to the total charge. No matter what values those three capacitors are, all different or all the same, all have the same charge, individual charge on each of them. Because if you look at that diagram, all of them have got 3 pluses on one plate, 3 minuses on the other plate. So with the constant value, capacitors connected in series, they've all got the same charge on them. Yep. It means calculate capacitors in series. So for capacitors in series, CT equal to, this might look a little familiar, the equivalent of the parallel resistor formula. Yes, see, that's C1. Pardon? So connecting them in series reduces the overall capacitance. The total is going to be less than the smaller one in the circuit. Sorry? Opposite, aren't they? The series resistors you add together. Parallel you do similar like that. Parallel resistors you add together. Series parallel capacitors add together. Series capacitors use that formula. The ground. C2 is equal. You can deal with numbers because they're all in microfarads. 1 over 30 to the minus 1. Sorry, not 30 to the ten. Yeah, like you get 3 30 ohm resistors in parallel. Just divide by the number you've got. But put that in your calculator. 10. And microfarads, yeah. T. or 100 microcoulombs. Yeah. Now, for saying there is for series capacitor, we one is equal to over 10 6 equals values now. Calculate the total capacitance like we did before. That'll be that's near enough, because that'll become 1,090 minus 3. It's close enough for what? Yep. The same for V1 times 10 by that 120 microfarads. 2 40 and 60. What do we get there? Kirchhoff's law, right? And a significant difference. So we should be here. That Daniel what? 91, 99 and all the odd bits 100. Yep. Yeah, he just... It's a small number anyway. Yeah. 1 would be better. You're rounding that to a single significant figure. Too much. So it just shows that danger. Yeah, depends how you've got your calculator set up. What's interesting, gents, to note, please, what's capacitor? See that? It's got one. 'Agreed? Well, charge goes up. For all of them, because it can't go above 100, can it? Right? In your, I gave you this one, principles. Because you can calculate. I need to do this because of the question. W is equal to 100 joules. It's there on that. So the formula